Good afternoon, everybody. My name is Matthias Schäfer. I'm with the University of Kaiserslautern in Germany, and I'm going to talk about secure track verification. To start, I'm going to give you a short introduction how the future air traffic surveillance system will track airplanes. That's a technology called ADS-B, and it's pretty simple. The airplanes are simply flying and broadcasting their positions periodically. And ground stations, for instance, or other airplanes, but I'll look at ground stations. Ground stations can receive these position reports and then process them and then show them to the air traffic controller, for instance, so that he can basically have a look at the current situation and base decisions on this data. So, but as the aviation industry usually puts lots of efforts in safety rather than security, there's no security involved. So these position reports, they are not authenticated or encrypted or anything. So we came up with this simple attack scenario. You have an attacker, and the attacker can simply inject fake position reports. What then happens is that the air traffic controller suddenly has like points on his screen that are actually not there. So he bases decisions, maybe critical decisions, on fake data. And that brings me to the problem that we try to solve with secure track verification. We try to answer the question whether a claimed track, so a sequence of location claims, is actually true. So is the airplane actually flying there? Those of you familiar with location verification might now think, all right, this has been solved during the last decades several times, and you're absolutely right. You could do a point-wise verification of every single position, but in the context of this aviation scenario, this is a bit problematic because these solutions for location verification, they have certain properties that make them unsuitable for this scenario. So for instance, you have distance bounding protocols where you use some sort of challenge response protocol in order to derive a upper bound on the distance between sender and receiver, and you can, by doing so, you can verify the distance. Well, but this problem uses like dedicated messages, like messages that are dedicated to location verification. And in aviation, you cannot simply change protocols. So if you introduce a new technology in aviation, that lasts about 20 years. So you have 10 years of design and certification and another 10 years of deployment, of global deployment. So that's not an option, at least for the short term. The second category of protocols, of solutions to location verification problem, they measure certain properties of the received signals, and then they check them basically for consistency, such as the angle of arrival, for example. And they check whether the signal comes from the right direction. Okay? As one of the main objectives of ADS-B and the future air traffic surveillance system was to reduce the cost, and for these kind of and you need specialized hardware for this kind of protocols, this is more or less counterproductive to this objective, right? There's another popular solution to the problem, like where you have a set of synchronized antennas, and by measuring the time difference of arrival of a signal at the different antennas, you can basically estimate the origin of a signal. But this again requires very tight time synchronization, which is expensive again, also counterproductive when it comes to costs. Yeah. There are also solutions that establish security by limiting the adversary's knowledge. So they assume, for instance, you have hidden base stations, and they assume that the position, the exact position of the receiver is not known to the attacker. Well, while this might work in some military scenarios, this won't work in the civil aviation scenario because you have so many players in the game, right? this kind of security by obscurity, well, not a good idea probably. However, the last point that makes these location verification solutions unsuitable for this problem is that we have an inherent mobility here. So the airplane cannot stand still until the protocol run has finished, right? It is moving all the time. And in fact, this property turned out to be really beneficial for us. So while the intuition might be, all right, suddenly instead of verifying a single position, I have to verify a sequence of position, you might think that's a harder problem, but in fact it turned out that you can actually get rid of all these previous system requirements by including this mobility into your scheme. So how did I do that? What happens when the airplane is moving while it's claiming positions? The distance to the receiver changes constantly. So you have a different distance for each location claim. And this results in an effect that, this constant transmission rate gets, from the view of the receiver, somewhat distorted because the propagation delay of the signal changes for each location claim, right? This effect is called the mobility differentiated time of arrival. And yeah, if we have a little closer look on it, we can set up a very simple relationship between this message inter-arrival time at the receiver and the inter-transmission time at the transmitter. And therefore, we look at the inter-transmission time, which is delta ij for two location claims, I and j, and we have the inter-arrival time, so the duration between the arrival of two claims, which is at the receiver x, which is denoted by delta ijx. And we have the two propagation delays of both location claims, which is delta I and delta j. And we can simply set up the following relationship. So the inter-arrival time equals the inter-transmission time plus the difference in propagation delay. Okay? So that is the simple relationship, which basically describes this effect I just mentioned. And if we put this equation in a security context, we can distinguish between trusted and untrusted values. We trust the values that are derived by the receiver and cannot be tampered with by the attacker, which is, in this case, the time of arrival measurement, so the inter-arrival time, okay? That we assume that the receiver is not compromised, of course. So, and all other values, they can be controlled basically by the adversary, by adjusting transmission times or claiming false positions, okay? All right. And our idea now was, what happens if we simply check this equation? So if we simply check what I see, is it what I should see, right? Based on the data that is claimed by the prover, by the moving object. So if you have one receiver, this does not establish any security at all, because as you might see, the attacker can simply adjust the transmission times so that the position reports, the location claims, arrive at the receiver as it expects them, okay? So this does not help us at all. But if we add two more receivers at different locations, we can formally prove that if all receivers independently check this simple equation, the attacker will violate this equation at least one of the receivers. And we can formally prove that, so that's a very nice thing actually, because this equation can be checked independently of all other receivers, so that means we don't need any synchronization. between the receivers. We don't need any synchronization or additional communication between the receivers and the airplane in this case. So it's a completely passive scheme, and that's actually pretty cool. So by including this mobility, we managed actually to get rid of these system requirements. Yeah, but all of you know probably that there is usually a gap between practice and theory, because in practice you don't have like perfect measurement values. You always have some noise in your measurements, right? And in our case, you have a little noise in the position reports due to, for instance, GPS inaccuracies. You have measurement noise when you measure the timestamps, the time of arrivals, and so on. And we summarized all these random noise sources in a normally distributed random variable. And we added another source of noise, which is the clock drift, which influences basically the transmission rate and, of course, what the receiver expects. And with this noise model in mind, we extended this basic verification scheme where we simply check these equations in a way that we use all location claims we've received over a certain period from a prover, from a mobile prover, to reduce this measurement error in our check for consistency. Okay? Therefore, we start with estimating the clock drift by taking the mean linear deviation of the left and the right-hand side of this equation. And in the second step, we calculate the mean squared deviation of the left and the right-hand side over the whole flight by looking at all pairs of position reports we've received so far. Okay? Over all i's and j's. The question now is, this verification value I end up with in the end, does it allow us to perfectly separate fake flights from real flights, right? That's what it's about. So we did some simulations where we took 1,000 tracks from the database of the OpenSky network, which is a project that monitors air traffic for research purposes. And to these tracks, we added all data we needed by simulation, the timestamps we needed, the noise, we added the noise. And we run a simulation using this data for two cases, one where the tracks were fake and one where the tracks were real. And we looked at the results, and we found that you can actually determine a threshold that perfectly separates. So what you see here is the false rejection and acceptance ratio. So what's the ratio of these thousand flights that was rejected falsely as being fake or accepted falsely as being real? Okay, and what we found is that if you observe the aircraft for at least 14 seconds, both rates drop to 0. So we can, after 14 seconds, we can perfectly say this flight is real or this flight is fake. All right? And that's actually a pretty cool result, because you can accomplish this without synchronization and specialized hardware, additional communication. This is a completely passive scheme, which brings me to the conclusion that we have shown that against all intuitions, you can use the mobility to make something better, to maintain a 100% detection ratio of such attacks without any synchronization, as a completely passive approach. We did not put any limitations on the adversary's knowledge, so this is no security by obscurity. Okay. And in fact, this solution does not only work in the aviation scenario. You can basically verify all moving objects, such as cars in a vehicular network or trains or whatever. You simply need a moving prover that reports its location periodically. There are still some open questions. For example, we assumed a stationary adversary. So what happens if the adversary is mobile? Preliminary results suggest that you can compensate this additional degree of freedom of the attacker by simply adding one more verifier. Another optimization possibility would be, what if the verifiers are mobile? So can we even improve our scheme by allowing verifiers to move? And this would be, for instance, if other airplanes are verifying airplanes, then you have mobile verifiers, right? And with these ideas, I'd like to thank you for your attention, and now I'm happy to take your questions. Thanks.
Hi. So you said you're not doing security through obscurity, so the attacker knows where all the receiver stations are.
You can fly home safely.
Sorry. Yeah. So the attacker knows where all the receiver stations are. But I think your proof is assuming the attacker is transmitting from one point. Couldn't the attacker just have 5 directional transmitters and just send the signal to different receivers
as all schemes that rely on time of arrival measurements, we are also vulnerable to attacks with a distributed attacker or a Dolev-Yao attacker that can basically perfectly determine when does which antenna receive which signal, basically. Yes, right. So this is still an unsolved issue. And that's a problem, as I said, of all schemes basically that rely on time of arrival measurements as ours does. Okay. Yeah. Thank you.
In one of the slides before you presented your schemes, you had several antennas and you had something based on time difference of arrival, and you said, oh, but that's too expensive. Then the solution you presented sounds to me like it is time difference of arrival. So is it too expensive or not?
I think I didn't get the question, sorry. Can you repeat it?
All right. In one of the slides before you presented your attack, you had several things that other people had done in the past decade which could not be done. One of them was several antennas that look like oil rigs. And you said, this one does time difference of arrival, but it costs too much because you have to have several antennas. Then it looks to me that the solution you are proposing also does time difference of arrival. So what is the improvement?
The improvement is that the antennas do not have to be synchronized anymore. Like what I said was that it's called multilateration, and therefore you need really tightly synchronized antennas, an area of tightly synchronized antennas, and in our scheme you don't need that. Every antenna can basically check this equation independently of the others. So, okay.
My question is, so your scheme relies on the plane to have a very constant broadcast rate.
Right.
Because like in other systems like AES, which is used in ships, the broadcast rate varies with the maneuver that the ship is currently taking, and I think there is even a random value to prevent repeated collisions. How does ADS-B deal with this, and is this rate really so constant and so precise that you can measure these differences?
Not really, but you can replace this constant rate with timestamps contained in the messages. So in the end, we just need to know what's the time between the transmission of 2 messages. And if the sender includes a timestamp in the message, you can determine it no matter which rate the sender is using. And in ADS-B, there is a mode which is rarely implemented where messages are UTC synchronized, timed to certain times of applicability, that's what they call it. And you can basically use this mode to estimate the duration between the transmission of two messages. How accurate that is, I don't know, because there is maybe 1 out of 1,000 transponders that supports this mode at the moment, because ADSB is still being rolled out. But in theory, it's possible. So the standard allows us to do that. So the scheme is perfectly compliant with the standard, actually, if the transmitters implement that accurate enough.
Okay, so we either need to change the protocol and include the timestamp,
Right.
or we need these transponders to have this very accurate retransmission time.
Exactly.
Okay.
Thank you very much.
So we should probably take future questions offline. Let's thank the speaker again, and let's thank all the speakers in this.